Okay, a couple things we might want to do with directed graphs here. Remember, with a directed graph, each edge has a direction, and you can only travel along the edge by that direction. So you could go from A to B, but not from B to A. So the first thing we want to be able to do is find all paths between two vertices, or explain why there aren't any paths. So let's say we're starting at D over here, and we're going to A, and we want to find all the different paths. So looking at D, notice we cannot go to E, but we could go to either C or H. Let's start off with going the path with C. Once we're at C, we could go to either B or G. Let's choose B here. From B, we really only have one option, and that would be G. And from G, we only have one option, that would be F. From F, we could go to B or to A. If we go to B, we're going to add in a cycle here, which we're not counting those as a path through the graph. We're counting only paths without cycles. So F to A would be one way. Then we kind of trace it back. If you're doing this with pen and paper, you can always make a note of whenever you made a choice. Let's just go back here. DC, we had gone to B. Let's go DCG directly. DCG, and then F, and up to A. Again, we don't want to add in the BGA because then we would add in a cycle there. Next, the choice back here was to go originally to C. If we had gone to H first, notice that we would have been pinned there. We couldn't have gone to C, we couldn't have gone to E. So really, D to C was our only choice at that option. And then we could have either gone B or G, and we've explored both of those routes, how to get to A from there. So there are two routes from D to A, and we've just shown them both. What about from B to H? So here's B, here's H. From B, we really only have one option, and from G, we only have one option. Here we could go up to A or B. No matter what we do, we're never going to be able to get out of this particular set of four vertices. We can never even get over to C because the only edges flowing between C and this portion of the graph are flowing from C over there. So there's no way we can get from anywhere on this side of the graph over to this graph. So impossible, because you can't, would be one way. You could word this different ways, but basically the idea is you can't get from this section of the graph over here. Can all points be reached from C? Let's do this by some coloring here. So I'm going to color this orange. And let's just color all the points we can reach from C. So we'll include B here. From C or from B, either way we could get from G. Once we get to a point, we don't have to follow a specific path. As long as we can get to one of these points, then we should be able to get to any point that it connects with. So C to H would be an option here. G to F would be an option. F to A would be an option. What else? Notice we can't get to D or E because all the directions are coming out of D and E. So this is as far as we can get. So can all points be reached from C? No. If we wanted to list the ones we could reach from C, A, B, F, G, and H could all be reached from C. But the answer there is no. So then the question is there any starting point that can reach all points? So we're not necessarily starting at C here. I'll leave this answer here as no. I don't know, you could try them one by one, but pretty soon you're going to realize that the hard place to get is over here with D and E. Once you can get to D, you could get to C, and we've already seen that from C you'll be able to eventually reach all of these points. So D could get you pretty much the entire group, but even D can never get to E. E itself has only outbound arrows coming from it. It's the only point in the graph like that. So from E, if we did start at E, notice that we could get to D and H. Let me just fill in D, for example. And from D, we could get to C. And then from C, we've already seen in this previous question that we will be able to reach all of these points once we get into C. So this gives us our answer that there is one and only one way, one starting point to give us all the points, and that would be E. So why does this matter? A lot of times directed edges can be modeling of real situations, so spread of a rumor or spread of a disease. So if for some reason this particular disease could only be spread in one direction, and you can think of there are ways that would occur. If a disease could only be spread in one direction, and if we know that one of these people started out with disease, and all of the people ended up with the disease, and we wanted to figure out where the disease came from, well, by using this type of question, we could see that the only one who could have started with the disease and infected everybody would have been person E. If C had started with the disease, he or she could have potentially affected this entire portion of the graph, but not D or E. Only by starting with E and following the edges along the one-way route could we eventually color in all of the vertices.